All right, so let's get back to our discussion of optimization. In this unit, we've been trying to figure out how to minimize this loss, which shows up in logistic regression. It's called the binary cross-entropy loss. We know that scikit-learn can do this, but we'd like to understand more about how it does that. And so first thing we need to do is, I guess to back up maybe, we said we have an algorithm called gradient descent, which is pretty simple. It just iteratively takes downhill steps. And if you take enough steps, you should get close to the minimum, assuming that this cost function is well behaved, if it's convex, and we'll talk more about that today. And it turns out that for this cost function, it is convex, and so gradient descent works well. And so our main task is to derive the expression for that gradient, because that's the main computational work, is computing that gradient every iteration. And then we said for these kinds of problems, which show up in machine learning, they have a particular structure, which is that there is this linear relationship between the weights we want to optimize and these scores z. And we can also write that kind of like this, where we have every score zi involves all of the weights. So what's complicated about this is that all these weights are sort of mixed together to get the scores, but what's simple about this is that it's linear. So that's the first stage. It takes us from W to these Z's. And then the second stage takes us from these Z's to the final cost J. And what's simple about that is that this cost is a sum of components which act individually on the ZIs. So here, there's no mixing across the ZIs. The only mixing is really just when they get summed together. But what's complicated is that this is nonlinear. So to summarize, we have like a two-stage pipeline that goes from our tunable weights to our cost. The first stage is linear, but everything gets mixed together. The second stage is nonlinear, but it is what we call separable. And so what we did is we realized that we can use the multivariable chain rule in this case, which says that if you're looking at the derivative of j with respect to a particular weight j, let's say this one here, you can kind of visualize this, the way that these variables are connected like this, where you have that particular w affects capital J through all the different scores zi. And so you can kind of see that there's all these parallel paths. For each one of those paths, it contributes this, which is like a dj dwi. And it's written in this two-stage procedure. There's a dj dzi and a dzi dwj. And the fact that there's multiple paths here is reflected in the fact that there's a sum in this multivariable chain rule. Okay, so armed with this approach and with the equations that determine the relationship between the zi and j, as well as wj and zi, we went ahead and we looked at those components, and then we plugged them into this expression. And we got, at the end of the day, a pretty clean way of implementing this. And we coded that in this function. And so this is a function that computes both the cost j as well as the gradient. And this function we need to call once for every gradient descent update. Then we realized that even though we were careful to not repeat computations unnecessarily, we were doing something suboptimal where you're recreating the A matrix every time we call the function. So then we came up with a different implementation using object-oriented programming, using a class where we have an initialization function that computes the matrix A. And then when we call the gradient, we can just use that pre-computed A. Otherwise, all this code is the same as before. And then the last thing we talked about is when you're doing these kinds of derivations, like this stuff, and when you're doing this kind of coding, it's very easy to make mistakes. And the really good way to debug your code is to check whether your gradient implementation is correct. And this application of our Taylor series approximation is a great way to do that. You create two different points, vectors W0, W1, that are near each other. And then you can implement this using the cost alone, this using your gradient expression, and these things better be equal to a few decimal places. And so for us, this works out, so we're pretty confident in our code. And let's see, I don't know if we got to this page here, but this is basically our gradient descent implementation. So this is really nothing more than a for loop over those iterations. And then when you look inside the for loop, you can see that, okay, so we initialize our weights somehow, usually randomly. And then in our for loop, it's pretty simple. We compute our cost and gradient given the current weights, and we update the weights using our gradient descent rule. So the new weights equal the old minus the learning rate times the gradient. And for debugging purposes, we are keeping track of the cost as well as the vectors W at each iteration. This is not really necessary, but it helps for debugging and for visualization. And really that's our code. It's pretty straightforward. Any questions so far? Okay, great. So this is what it looks like when we run things. So we're going to initialize just using zero mean unit variance Gaussians for our weights. And we're going to run for 2,000 iterations, and we're going to use a learning rate of 1e minus 4. And when we run our code and plot the history of the losses, notice we are plotting on a log scale for the iterations and a log scale for the loss. That's usually very important because if you don't do that, you get a very boring plot. The plot looks kind of like this. It looks like, suddenly the cost got very small, but really all the interesting stuff is happening down here, and that becomes visible once you plot the log both axes, and now you can see more clearly what's happening. So here's, 1 iteration, 10 iterations, 100 iterations, 1,000 iterations. We're stopping at 2,000. And you can see that the loss is making good progress. It is decreasing from its initial value, but you can see that it still seems to be going downhill at 2,000 iterations, which means we're not really finished optimizing. And when we plot the test accuracy, we get a value that's pretty decent, but can be improved. Okay, any questions so far? All right, so the key questions for us are, how do we choose the number of iterations and how do we choose the learning rate? So here you can see for this learning rate, we would need to use more iterations. And maybe we can do that. It depends on our computational resources. If we have really fast computer, maybe we can run for millions of iterations without a problem. But if not, maybe we're kind of impatient. We don't want to wait that long. So we would like to know, can we change the learning rate? Maybe we can speed things up. So if I want to speed things up, do I increase the learning rate or decrease it?
Increase it.
Increase it, that's right. Because we're going to be taking bigger steps downhill, right? We want to take bigger steps in the hope that we can get there faster. But as we know, if our learning rate is too big, we can take a step that actually increases the loss. In other words, we make negative progress. So let's do a little experiment where we try several different learning rates. So previously we tried this orange one, 1e minus 4. We'll try something that's an order of magnitude smaller, an order of magnitude larger, 1e minus 3, and then even a little bit larger than that. So the orange one, like we said, that's from the previous page. If we decrease the learning rate, you can see it takes even longer to converge. If we increase by a factor of 10, we get this green trace. And then if we increase that by a factor of 2 more, we get the red trace, where things are really going crazy. Okay, so when we look at the loss over here, this is like the first iteration, second iteration, third iteration. You can see that our learning rate is actually large enough that we are overshooting and making the costs larger at first, right? So that's not great. But then we do notice that somehow we eventually do make progress. In fact, we're sort of overall more efficient than the orange curve, even though we're not always decreasing. Sometimes we overshoot, but then sometimes we make a lot of progress. But you can see that we're really on the edge of where things go crazy, because if we just increase by a factor of 2 more, then we have this behavior where we overshoot a lot. And in fact, even here after 2,000 iterations, we continue to overshoot and never really get close to the optimum. So in other words, if we come back to this plot over here, not only are we overshooting, but once we get down to the vicinity, we just keep bouncing around and we never settle down. So we're never actually going to converge. We're just going to bounce around the solution. That's what's happening over here. Okay, so so basically what we learn here is that if the learning rate is really small, things are good and that there's no overshooting, but things are bad and that it takes many iterations to converge. As the learning rate is increased, things get better, but at some point we start to overshoot. And if we increase a lot, then things get really crazy, and in fact, it prevents us from ever really converging to the minimum. Okay. And if we look at the test accuracy, this is the loss. Remember, this is our training loss. This is the corresponding test. Things are pretty well tracking what we would expect. Actually, it's sort of interesting. So the test accuracy is equal for the orange and green. Sorry, orange and red. I guess that makes sense. They're pretty close. And the green trace, 1e minus 3, has the highest test accuracy. Okay, so any questions on this? Yes.
So since it's like there's only, was it convex? So
Yeah, this is convex.
They're all like trying to approach, or they all would be approaching the same
Minimum.
Minima. Okay, other than if it wasn't convex, then they could be approaching separate.
Exactly. That's exactly right. So because this is a convex problem, when the step size is small enough, we actually proved, right, that we're going to get there eventually. And that's great. We can have confidence that we can solve the problem if we wait long enough. But then sometimes we struggle with waiting long enough due to computation or due to being impatient. And then we might try to push things a little bit. And perhaps if we increase the learning rate a bit, sometimes we overshoot, but then at the end of the day, maybe we actually get there. Because it turns out that this cost function can have steepness or gradients that are different near the solution versus near the initialization. So if the cost function is steeper near the initialization, you'll get this overshooting there, but then if it's shallower near the minimum, there won't be any overshooting down here, right? So that, I believe that's what's happening. So even though it's overshooting at the beginning, it's doing fine down here. That just has to do with the shape of the cost function. But of course, if you push things too much, then it's overshooting. This red curve is overshooting everywhere, and it's never going to converge. Okay, but when we're dealing with convex losses, yes, like if you really want to be sure, you just use a small enough step size and you run for a long time. There are algorithms that will adjust the step size dynamically in a way that you can be confident they will converge. So I used to cover one all the other times I taught the course, but that kind of algorithm is really only appropriate for convex losses, which are not what you tend to find in machine learning. In kind of simple machine learning problems, yes, the loss is convex, but I didn't want to distract you from the real and more popular problems that we're going to start talking about, like what we have with neural networks and things like that. So I took out that material, but I should just point out that we could go down this path, make a little bit more progress by using a fancier algorithm that is able to dynamically adjust the step size on the fly and still get us convergence. But we're not going to do that because it's a little bit of a distraction, I think. For these kinds of problems, scikit-learn has a number of different algorithms programmed under the hood that you can select. And these are selected by experts that view them as very robust and the right algorithms. So we don't have enough time to really dive into more details, but you can try different algorithms if you're solving problems, convex problems like these. You'll find that some have advantages with larger data. Some have advantages when there's more features and less data samples, like one of the labs you had, where you had way more features than samples. Different classes of algorithms handle different problems. Some of those algorithms can handle the non-differentiability of the L1 regularization, some cannot. So there's really just a bunch of different algorithms that are out there for different cases. Okay, great. Any more questions on this stuff? Okay, so since we've been talking about convexity quite a bit, I thought I should, briefly just explain exactly what it is, and we'll not really, get into too many details here, but I think it's just good to know about since we recognize the importance of convexity. So what exactly is it? So before we talk about convex losses or convex functions, we need to talk about convex sets. So basically, a set, we'll call it D, is convex if for any 2 points in the set and any interpolation parameter t between 0 and 1, this linear interpolation of those 2 points, which is called a convex combination of the 2 points, must remain in the set. So here's some visualization. So here I have 2 points x and y in my set. The convex combination here for all these different t's would be this line segment between them. And we need that line segment is completely contained within the set. And you can see for that x and y it definitely is. You can also imagine that any other 2 x and y that you choose in the set, if you draw all their convex combinations, they're definitely going to be in this set, right? So this is a convex set. But down here, we have an example of a non-convex set where we have these 2 points. We draw their interpolations, but this interpolation, you can see, it is outside the set for some points, and so that would be an example of a non-convex set. Okay. So basically, in words, you want that the line between any 2 points in the set remains in the set. Okay, is this notion of convex sets pretty clear? Okay, great. So here are some examples of convex sets. There's many, there's just a few. Like a circle is a convex set, a square is a convex set, an ellipse. The set of all n-dimensional real vectors is a convex set. If you have a hyperplane in Rn, that's a convex set. If you have a half space in Rn, that's a convex set. What do I mean by a half space? So in a one-dimensional set, that would, normally this would be the whole real line. A half space would be at 0. I consider, let's say, only positive numbers. And so that would be a half space, or like in 2 dimensions, I could look at half of the entire space. So these are just examples of convex sets that occur pretty often in machine learning. Any question on convex sets? Okay, so now that we know about convex sets, we can talk about functions, convex functions. So a function f is convex, number 1, if its domain is a convex set, and number 2, if for any 2 points in that domain and for any interpolation parameter t between 0 and 1, if the function applied to the interpolation between x and y is less than or equal to the interpolation of the function applied to x and applied to y. So in other words, if you do this, you could say interpolation at the input to the function, this should be less than or equal to what happens if you do the interpolation at the output of the function. And so here's a picture. We have a point x here. We have a point y here. This is just on the real line. So this is just a function of real inputs. And then here, t is, I don't know, maybe t is like 0.7 or something. So here is our linear interpolation of the inputs. So we need to look at the function at that value, and the function at that value would be this. Right? So this is if I do my convex combination on the inputs and I evaluate the function there, that must be less than doing my convex combination at the output of the function. So in other words, this is the value of the function at x. This is the value of the function at y. I can do a convex combination in this axis here, at which point I would get like this. So I need that this value is always greater than this value. So essentially we're looking for functions that are kind of curving down. It would be fine if the function is even like flat. That's fine too. But if the function is going up, then we don't have convexity. Because when we look at the linear interpolation of inputs versus outputs, we run into problems. So this is what it means for a function to be convex. Is this making sense, or any questions on this? I think you guys have probably seen convexity before. I think even like in people talk about convex versus concave as being like, curved like that versus curved like that. So this is just the technical definition of it. Okay, so here are some examples. If I have a one-dimensional input, scalar input, and I have any kind of linear function, that would just be, a line that is convex. Basically, you have an equality in that case, but that counts as less than or equal to. Now, if we grow x to a vector and we make a linear function, notice we're always talking about scalar output functions, never more complicated. So in this case, we need to do some linear combination of our x's and then add another offset. So these functions are always convex. When we look at quadratic scalar functions. They are convex if and only if the coefficient on the squared term is non-negative. That's when you get a parabola that is curved up or possibly flat, but as soon as a goes negative, you have downward curvature, and that's concave, not convex. Okay, so if we extend this idea a little bit, again, scalar x, if it's a general function but the second derivative exists everywhere, in other words, for all x. So if the second derivative exists everywhere and is greater or equal to 0, then this is a convex function. So that's kind of clear here. If you took the second derivative, that's just going to be a, so that's where this requirement comes from. If you want to look at vector-valued functions, then you replace this second derivative with the Hessian matrix, and the analogy in terms of positivity or non-negativity for matrices is positive semi-definiteness. So we talked about that back in the linear algebra section. So you need a Hessian matrix that is positive semi-definite. Other things that we often see, norms, these are always convex. If you have two convex functions and you add them together, the result is also convex. Another interesting question is, what if you have two convex functions and you chain them together? You look at their composition. Well, it turns out that that is only convex if the second one is non-decreasing. So in general, chaining convex functions together does not give you a convex function, but it is in the special case that the second one is non-decreasing. And finally, in terms of things that we have seen in this course, RSS, binary cross-entropy loss, and their L1 or L2 regularized versions, those are all convex functions. So that's why everything we've worked on so far is convex, and it is simple to optimize, relatively simple compared to what we'll start doing later today maybe. Okay, so that's convexity. I just wanted to kind of define what it is. And I guess we have one more page here, which is stuff I've been saying for a while, but it goes like this. So if you have a convex function and you can find a local minimizer of it, then you can be sure that that is also going to be a global minimizer of the function. So whenever this small step size gradient descent converges to a local minimizer, you can be sure that you've also found a global minimizer. And the function, may be, this theorem could be, this theorem doesn't necessarily need differentiability. So if you have a non-differentiable function like this, that's convex, but non-differentiable, the theorem also holds, except gradient descent is not going to be the algorithm we want to use on that because it's not differentiable. Essentially, gradient descent, if you apply to this kind of function, would just bounce back and forth, and it would never settle to that point. There's ways to fix it, like if you decrease the step size over the iterations and so on, but generally speaking, you want a different kind of optimizers for those kinds of non-differentiable losses. Okay, so that's really all I wanted to say about convexity. Are there any questions about convexity? Okay, great. And there's just one other topic I wanted to briefly talk about because sometimes it comes up in this course, which is constrained optimization. So until now, all of our optimization problems have been unconstrained in that they have the form like arg min of w of some j of w. So we're just looking for any combination of parameters w that minimizes that function. But sometimes there's additional constraints that we put on these w's, like we might say that W transpose A, which is some linear combination of the weights, maybe this must be greater or equal to some number B. So that would be an example of what we call a linear constraint. In that case, you can always rewrite the linear constraint, in this case, let's say by moving, I wanted to make this equality. You can always rewrite this by moving the B to the other side and equating with 0. And then we can think of this as some function h of W. Okay, so this would be an example of an equality, a linear equality constraint. You can also come up with nonlinear equality constraints, and you might actually have several of them. So maybe you have several combinations of A and B, and so you actually get several of these HWs that you want to equal 0. So that's what I've written here. You have HLW equals 0 for L going from 1 to L. So in this case, several equality constraints in the problem. Now, some problems also have inequality constraints, which you can also write relative to 0 for the same reason. You just kind of massage them until you have 0 on one side. Okay, so for these kinds of problems, there's a really elegant way to solve them. So here's how you would write the constrained problem. So here you want to arg min the cost or loss such that our constraints are satisfied. To handle this, we're going to reformulate the constrained problem as an unconstrained one involving additional design parameters. So let's first talk about the case of equality constraints. So here's what you do with equality constraints. You take your original loss, and then you add on a new loss, or regularization, or whatever you want to think about it as, a new term that has these new parameters, lambda, one lambda for every one of these constraints. These are just real numbers. And just multiply those lambda L's times the H's. And you call this a new loss that is now something you have to optimize both over W and the vector of these lambdas. But now you can just treat this as an unconstrained problem. So for this, we have methods to solve it. Is that idea pretty clear? These lambda are called Lagrange multipliers. How many of you guys have seen Lagrange multipliers in a previous course? Okay. So the reason this works is that, remember, whenever we have a problem like this, where we have differentiability with respect to a parameter, we know that we can set the gradient or the partial derivative with respect to that parameter to 0 at the optimum, right? So let's consider what happens with our lambdas. Let's say we force the derivative with respect to lambda L to 0. Well, what is the derivative with respect to lambda L? It's just going to be HL. So by forcing the derivative to 0, we are implicitly forcing HL to 0, and thereby enforcing our equality constraint. So that's why this works. You're just writing it in such a way that the standard definition of a stationary point enforces the equality constraint. Okay, so that's Lagrange multiplier approach. I'm pretty sure we're going to see this in the tree unit, not the next one, but the unit after that. Now, if you have, this is for equality constraints. If you have inequality constraints, the idea is similar, but it's just a little bit more complicated. So here is how we're handling our equality constraints, identical to here. But now I've added another term to handle the inequality constraints. The term has the same form. You have some new parameters, mu, that are just multiplying those inequality constraints, and now you have to optimize over W, lambda, and mu. But there's a few additional conditions that need to be satisfied on the mu's, and so those things are described by what are known as the KKT conditions. And it's a little bit complicated, so I'm not going to get into the details. But if any of you guys ever need to work on these kinds of problems, this is exactly how they're solved. So, you can click on these links and read up on some of the details, or take an optimization class that teaches you those tools. And so that's all I wanted to say about constrained optimization. There are techniques to solve these problems, and basically they reduce down to an unconstrained problem, which we have good tools to solve. Okay, any questions on constrained optimization? All right, so last thing is a few things that we will talk about in coming units. So we're going to be talking about a version of gradient descent that is sort of the real workhorse for machine learning, called stochastic gradient descent. We're going to talk about that in the next unit. And we will talk about some practical strategies for applying those strategies to non-convex problems. But there's many things that we won't cover in this course. I mentioned today these adaptive step size algorithms. We're not going to get into those details. There is a fancier class of algorithms than gradient descent called Newton's method, which instead of a scalar step size, you could think of as having like a matrix step size that involves the Hessian of the function you're optimizing. We're not going to get into the details of non-differentiable optimization, what we need to solve things like lasso. And then there's other algorithmic enhancements like momentum that we won't really dive into the details of. But you can find these things discussed in other courses here at OSU. So a few of them would be 5500, Intro to Optimization, taught autumn every year. This is a very kind of broad, useful optimization course. Then we have 6500, which focuses on convex optimization and all those specialized strategies. And then finally, we have more of an advanced course on non-convex optimization for machine learning, which is taught autumn even years. So just sort of, these are the places you can learn more if you'd like to. And if you're getting into this field of machine learning, these are definitely important courses. Okay, so that's all I have for this unit. Any questions on anything? Okay, great. So we can then jump into the next unit, and I think this is where things start to get really fun in this course, and we start to get into topics that are much more modern and relevant to things that are going on today. So we're going to start talking about neural networks, and we're going to basically just consider a really simple problem and different ways to solve it that are going to lead us down the path that leads to neural networks. So here we have a classification problem, binary classification. We have labels that are either 0 or 1, and in this picture they're either blue or green. Our features now are just going to be two-dimensional, so we can visualize them. So we have like x0, x1, and we have a scatter plot. And so you can see we have a non-linearly separable data set. There's no way that I can form a classification boundary that's linear in this space and cleanly separate on one side of the line blue dots and on the other side of the line green dots, right? There's just absolutely no way to do that. So if you applied logistic regression to this data set, it would fail miserably. It wouldn't give you anything reasonable. So what do? Okay, we have talked about the idea of applying nonlinear transformations to our features before we apply our linear methods. So we saw all this back at the end of Unit 2. We said, if I have a scalar feature, I could maybe take it to different powers, x squared, x cubed, and so on, polynomial. And that's where we could still apply our linear methods, but we got much more complicated predictions. The prediction function in the raw parameter space was no longer linear. It was like a polynomial function. So that is definitely something you could do with data sets in general. And so one idea that works well if you just want to try something simple is for every 2 features in your data set, in addition to using those features in their raw form, you could imagine squaring each of them individually, and you could imagine taking the product of those 2. So basically what we're saying is you have, from 2 features, now you've created 6 features, and now you just treat these as new features and you apply linear classification using those features. And of course, you can go farther. You can take this to, 3rd power as well. You could, put a square on one or a square on the other, or the sky's the limit, right? You can do as much as you want. You can create crazy new features. But as we know, it's not always fruitful because of what? What's the issue that we have when we have too many features? What do we call it? Overfitting, exactly. We have features that are distracting us more than they're helping us. And so what's going to happen is our bias will go down, but our variance will go up dramatically. And so we originally saw this in the context of polynomials with model order selection, right? We said, yes, you can create like polynomials with arbitrarily high powers, but as the power gets higher, the training error goes down, but the test error starts to go up. So then we talked about model order selection, like where do you truncate your polynomial? And then in Unit 4, we went another step. We said, okay, we can actually do better. Rather than just truncating the polynomial, we can actually pick and choose certain polynomial coefficients to use and ignore the other ones. So that's feature selection. So that's something you can do here too. And if you just create these basic features and then you apply feature selection well, you'll be able to extract, hopefully a few useful features. And from what I've seen in previous course projects, this can be pretty successful if you do it right. You have to do the feature selection right and so on, but it can be pretty successful. Of course, you can see this is kind of a blind approach. It's sort of, it's not very sophisticated. Kind of like a shotgun approach. You're just trying a whole bunch of stuff and then trying to prune things with feature selection. If you are very clever and you know something about your data set, sometimes you can add maybe just even like one additional feature that makes everything magically tractable. So let me give you an example with these pictures. It's a little bit hard to see, but these are blue points here. So these are points from one class. These are points from the other class, a red class. And just in the raw feature space, so we have features x0 and x1, you can see that this is definitely not linearly separable, right? So logistic regression on that would not work. But let's say, this is the origin here. So what if I add one more feature, which is basically the squared radius, x1 squared plus x2 squared. So now I'm going to have 3 features. And if I plot my data according to those 3 features, now you can see that the 3rd feature, which measures how far we are from the center, is large for all the red points and small for all the blue points. And so if I applied logistic regression here, it would work fantastically because you can see this is a linearly separable data set, right? I would just put a hyperplane through there, boom, perfect classification. So the point is that these nonlinear transformation of features can be incredibly powerful. They can allow you to apply simple methods to more complicated data sets and just have them work. But the hard part here is choosing that feature transformation. If you don't really know how to choose it, you're just kind of searching blindly maybe for something that works. Maybe you never find something that works great. Okay, so that's the idea behind feature transformations. Any questions so far? Okay, so the idea behind neural networks is basically to learn a feature transformation that works well for your particular data set. That's the whole idea. Okay, so what we're going to do is we're just going to start with a really simple idea, kind of a heuristic idea, to solve this data set. And as it turns out, this heuristic idea is one way to understand a very simple neural network. So this is the idea. We're going to have a two-stage approach. In the first stage, we are going to generate our transform features. In the second stage, we're going to do standard linear classification according to logistic regression. We're going to learn 4 transform features. So, similar to how here we went up in dimension from 2 up to 3, we're actually going to go from 2 up to 4. And the way we're going to create our transform features, there's obviously many, many ways to do it, but the way we're going to do it is we are going to create them as soft outputs of a linear classifier. So what do we mean by this? So remember when we talked about the hard outputs of a linear classifier, it might be like the numbers 0 and 1, if those are my classification labels. Whereas the soft output is basically the probability that it's 0 or the probability that it's 1. Meaning the probability is going to be a number in the interval between 0 and 1. So that is what we mean by a soft output. And if you remember the equation from logistic regression, the probability that y equals 1 given the linear score z is basically going to be e to the power z over e to the power z plus e minus z. Or you can write it different ways. You can write it as 1 over I'm trying to remember how exactly we wrote it, but let's see. We can write it. Oh, sorry. I meant to. Yeah, it depends if we're doing labels plus minus 1. So in this case, since the labels are 1 and 0, we would write it like that. So, and this, if you remember, when we plot this, this is our sigmoid. So here we're plotting versus z, and the probability is something that looks like that. So it crosses at 0.5 there, and it goes between 0 and 1. Z, if you remember, Z is our linear output. Z is our weights. W transpose our input. Okay, so is this ringing bells? Back from Unit 5. So in this picture, remember when we talk about linear classifiers, we can think about them in terms of their decision boundaries. So for example, this will be one of our linear classifiers. And we know that as you move, if you're looking at a point directly on this boundary, you get z equals 0. And that means if you plug z equals 0, you get probability 0.5. Right? So the soft output along that line for that classifier is going to be 0.5. Now, as you move in one direction, you will start to increase. And we don't actually know the direction where things increase, whether you go up this way to increase or down. It really depends on what happened in the training. But let's just say, for sake of argument, that when we go this way, we increase to 1. And when we go this way, we decrease to 0. Right? And if this transition happens pretty quickly, we can say, roughly speaking, that for this classifier, all the points on this side are approximately 0, and all the points on this side are approximately 1. Okay? So that's one of the 4 linear classifiers. So then let's say we have this one. Maybe for this one, all these points are 1, all these points are 0, and so on. Same thing for this. And so at the end of the day, when you look at those 4 numbers together, you'll notice that this region, and in that region only, they will all be positive together, right? And in all the other regions, so this is like 1, 1, 1, 1, and here it might be like 1, 1, 1, 0. And over here it might be like 1, 1, 0, 1, and so on. Okay, so we've created these features. These are the nonlinear transformation we're creating, we've created these features so that it's maybe not that difficult to recognize where the green points are. In particular, like if we just have a linear classifier and we set the weights of our linear classifier proportional to the all ones vector, it is going to give us the largest score for the points in here. And for the points outside here, it's going to give us smaller scores. Okay, and so we can also put that final output through another sigmoid to get a probability, and this is what we get. So this is being shown as a heat map. So where you see the dark red, that means that the output, soft output, is close to 1, and when you see close to white, that means it's close to 0. So our final two-stage method is predicting, that the points in this region are green with probability close to 1, and the points out here are blue with probability close to 1. Is that idea making sense? Yes.
Why does the sheeting, I get the heat map, but only the third one looks correct in your explanation?
Yeah, we haven't talked about this yet. So I was just trying to explain the idea in, let's just suppose for our first explanation, we imagine that this sort of pattern of 4 numbers is all ones here and is not all ones outside there, right? So then, yes. Does everybody see how that can give us useful features for classification? Okay, good. So now, we did not choose those boundaries. We didn't put them there manually. This is what happened when we trained this system. We kind of set it up to come up with some soft outputs and then to use those soft outputs for linear regression. And it doesn't need that these numbers are all ones. Really, it just needs to be a unique pattern. It might be 0, it might be 0, 1, 0, 0. It could be anything. Anything is going to work as long as the outputs in each of these are distinct. And so now when we look at these heat maps, we can see what actually was learned. So this is the soft output from the first classifier, which ends up being this one, you can kind of see. And it turns out that according to the heat map, the ones are on this side and the zeros are on this side. Okay, and then for this second classifier, which ends up being this one, the ones are here, the zeros are there. And the third classifier, which is this one, you can see we have ones here. So finally, at the end of the day, you can see the actual pattern learned was a 0, a 1, and a 0 for that inner region. Maybe I'll write that down. 0, 0, 1, 0. Okay, so that was the pattern that it assigned to the center. And then when you look at the actual weights that were learned, those are also printed up here, have -5, -13, +12, and -12. And you can see that the signs here are always going to cancel. So whenever you have a 0 here, you're going to have a negative sign. Whenever you have a 1 here, you're going to have a positive sign. So these weights that it learned were consistent or aligned with that pattern. And since this was started from a random initialization, if you would redo this, if you run this demo code again, you will likely get a different pattern, but you will always see that the signs of the weights are going to match up with the pattern that you learned. And these boundaries will be also different with a different seed, different random seed. So this is the main idea behind this two-stage approach. Is this sort of making sense? Okay. So here's a question for you. Did I need to use 4 transform features? Could I have used 3 based on your understanding of what's happening?
Yeah, but it would have been less accurate.
Okay, what would the decision region?
Like if we got rid of the orange line, you would then,
It would be shaded triangle.
Yeah, but you can see it's possible. We could have made something that gives us a contained center region, right, with 3, right? So may not have worked as well as 4, but it would have done something useful. What about 2? Could I have used 2 features? No, right? Because there's no way I could put 2 lines that are going to contain the green but then block out the blue. Okay, what about 5? Sure, right? The more features I use, like the more control I have over my region. Okay, so that's right. So you can see that the choice of the number of transform features is somewhat flexible, but there is kind of going to be a lower bound. If you make this thing too simple, it's not going to work. But if you make it too complex, what do you think is going to happen? Overfitting, exactly. There's actually a very interesting twist on this that we'll talk about next time. But yeah, that's the intuition we have from the bias variance trade-off, at least. Okay, so that's the approach. We'll dive more into details next time, but this is going to give us essentially a 2-layer neural network. All right, we'll see you guys on Friday.